the last video that you're going to watch that's going to help you solve genetics problems. And in this case, we're not going to use Punnett squares. Instead, we're going to look at the genetics through generations of a family. And to do that, we're going to use something called a pedigree. So basically, this is pretty simple because a pedigree is just like a family tree. But there are some rules that go with pedigrees. Females are always shown as circles, males as squares. And if you see a shaded individual, that means that they are affected by a trait. Now, there are also some rules that you need to learn about how to label and read a pedigree, and I want you to focus on these. Each generation is given a Roman numeral. So, for example, this would be generation 1, this would be generation 2, and this would be generation 3. And then the individuals within generations are given regular numbers. So 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. And you can see I started over with each generation. This allows people to discuss the pedigree and say things like, well, individual 2, 3 is affected by the trait. And then we all know we're talking about this male right here. So you can use pedigrees to help, or you can use them you can use pedigrees to help understand patterns through generations, or you can use them to just take place of a Punnett square. And some of you that are starting to do Punnett squares in your brain may actually be visualizing them in this way. So, for example, in this pedigree, we're tracking the trait of night blindness. So, night blindness is a recessive trait. It shows me here in the key. Normal vision is dominant. So, I could ask you to write the genotypes of the individuals, and I might ask you what possible individuals could be if we don't know what their genotype is. So what I think the easiest thing to do here to start with question 1 is to write out all the people that we know to be homozygous recessive. So anyone that's shaded we know is little n, and we can write that on the pedigree. Shaded individuals are the easiest ones to figure out. And then the rest of the individuals we know must be either big N, or big N, because they aren't shaded in. They have normal vision, but we have to kind of figure it out. It's kind of a puzzle of if they're homozygous dominant or heterozygous. So we do that by looking at the parents. It's important that you remember that anybody's genotype has been determined from inheritance from their parents. That if you are big N, little n, one of those came from your mom and one of those came from your dad. So let's look at individual 1, right here. We know this person could be either homozygous dominant or heterozygous genotype. So we know basically that they would be N blank. But looking at their children, this child right here, this daughter, little n, one little n came from the mom, but one little n must have come from the dad. You can't get both of your letters from one parent. You have to get one from the mom and one from the dad. So we can know that there's a little n. In that same manner, this person's brother and sister, we also can know. So in our minds, first they start out as big N blank. But we realize that all mom can give them because she's shaded is little n's. And so in this way, we can fill out the pedigree. We come over here and we realize that this woman must have a recessive letter. We come over here, we realize this woman must have a recessive letter because of her mother. This man here must have had a little n because of his daughter. This person, so we go through and we fill in as many as we possibly can. Now there will be some individuals that we cannot determine for certain. For example, individuals 1, 3 and 1, 4 we cannot determine for certain because neither of their children have the recessive trait. So there will be some people where you cannot determine their genotype. And in this case, what's best to do is to just leave them as an N with a blank. Because that will show me that you understand that they must have at least one dominant allele. Oop, sorry, that one we can't determine. But you can't determine anything else with the information given. Now, question 2 says if individuals 2, 2 and 2, 8 were to marry, so let's identify those. 2, 2 is right here, 2, 8 is right here. What would be the possible genotypes of any children they might have? So we can do a little Punnett square. big N, little n, little n, little n. And you might be doing these in your head by now, but if you need to, just to double check, go ahead and write it out. So the possible genotypes that the children could have would be big N, or little n. Now I can also give you pedigree problems where it is a work backwards situation or a guess and check situation such as this. I might give you a pedigree and ask you, could this be autosomal recessive? Could this be autosomal dominant? Could this be X-linked? And you would have to go through for each one and determine if it could or could not be. So for example, if this was autosomal recessive, this person would be little n, that would work because we could have the parents like this. So this would be yes, and I could show my work, guess and check, just like that. Okay. Autosomal dominant would mean that this person would have a dominant trait. Well, these unaffected people would have to be the recessive traits. Now looking at these parents, if neither of these parents have the trait, all they can give is little n's. Can they have this child? No. X-linked, we're going to have to be careful because we remember the squares are the males and the circles are the females. So we'll have to do XY, XX, XY, XY, XX, XX. And it says recessive, so this person would have a little n. Now we know that this person had to inherit the trait from someone. Now the father could not have donated that X. The father only donates the Y. Also, if this person had a little n, they would be shaded in. So we know that the unshaded males must have the dominant letter. But this woman could be a carrier. And in that case, this person could exist.